So after you write out the quotient rule, which is f prime x g of x minus f of x g prime x over g prime x squared, f of x is x plus 1. G of x is x minus 1. So f of x is the numerator. G of x is the denominator. Okay? And f prime x is 1. And g prime x is also 1. So you get y prime or dy dx, whichever way you write it, is 1 times g of x, which is x minus 1, minus f of x, which is x plus 1, times g prime x, which is 1, over g of x, let's see, wait. I think it's g squared, right? It's not g prime, it's g squared, isn't it?
Yeah.
Yeah, I wrote prime in there by accident. It's g squared. So I'm going to have g is x minus 1 squared, right? So,
This is where you're basically reducing, like, for example, for the f prime of x, for the first one,
uh-huh.
you're basically making x to the 0 power. Is that right?
Yeah, essentially, the derivative of x with respect to x is 1 because x to the first means that you have 1x to the 1 minus 1, right? So when you do the derivative, let me open up a Google Doc and show you. You're talking about the power rule, right?
Yeah. Just how you
So,
found f prime of x to be 1.
so if yeah, well, there's two rules. I mean, it's basic property, but you can do it using the power rule.
Okay.
There's if you're not quite sure, you can even not I would at this point, but because you've only been doing it for a couple of days, if you think about the power rule says something like this. It says the derivative with respect to x of where's the bracket? There it is. X to the power of n, okay, is equal to n x to the power of n minus 1.
Yeah.
Okay? Right. So if you are doing the derivative with respect to x of x, okay, that's like saying the derivative with respect to x of x to the first power. Okay? And if that's true, by the pattern, then you get 1, right? Because n is 1, x to the power of 1 minus 1, right? Do you see
Yeah.
that?
Mm-hmm.
And then you get, this is equal to 1x to the 0 power, and then we have to use our exponent rules. X to the 0 is 1, so now we get 1 times 1, which is 1.
Okay.
So Now you're doing the derivative with respect to x of, well, you're doing both, but you're doing x plus 1, right?
Uh-huh.
This is like doing the derivative with respect to x of x plus the derivative with respect to x of 0. Okay? Now, the derivative with respect to x, we did on the previous line right here. That's 1, right?
Yeah.
The derivative with respect to x is 1. The derivative with respect to x of a constant is 0. Now, because there is no x, okay? So that's just equal to 1. And the derivative of a constant, because that's another property. There's two properties. I mean, you can do it this way if you have to, but two of the limit laws that you should really learn are the derivative of x or any variable. When the variable down here in your denominator of your integrator, the dx, matches the variable here, you get 1. So d dy of y is 1. d dx of x is 1. d dt of t is 1. When they match, it's 1. So
Okay.
when they don't match, we're doing something called implicit differentiation, but we learn about that in chapter 3. But when they match, it's 1. So here, this is always 1, and the derivative of a constant, d dx of a constant, your book might write it differently. Oops. Is 0. So, oops, what was that? There we go. It's changing it. I don't know why. It doesn't like it. Okay, fine. It's changing it to the copyright sign. How weird is that? All right, I'll get around that. How about that?
No.
All right, there's one. Undo. Thank you. Undo that, and let me go on with my life. Okay.
There we go.
0. There we are. Okay?
Okay.
So, meanwhile, we're here. Okay, so are you okay with what I did?
Yeah, I was just wondering for the top, did you have 1 times x minus 1? Is that right?
Yes.
Okay.
Minus.
Minus the x plus 1 times
Right.
1
Over what?
over x minus 1 squared.
Perfect. Beautiful. Okay. Beautifully done. So now, we're just going to simplify. X minus 1. Remember, you have to take the negative through the second part. So minus x minus 1 over x minus 1 squared. Yes?
Yes.
And so y prime is equal to, be careful, the x's cancel, right? The 1's don't. So you have negative 2 over x minus 1 squared. Okay? Now that expression, negative 2 over x minus 1 squared, that is the expression, the general expression for the slope of your tangent line. Okay?
Okay.
That's the expression for any slope.
So we could technically use this if we have like a quotient or
Used what?
like he was saying that now that we know how to do these derivatives, we could do it this way instead of doing it the other way.
Instead of doing f of x plus h minus f, yeah.
Yeah. Okay.
Unless he specifically tells you, like on the quiz or the review, I mean,
Yeah.
if he specifically tells you to use the definition, then you have to go back to the limit as x approaches 0 of f of x plus delta x. Whatever version you learn, there's a couple of different versions. There's one with x plus delta x. There's one with x plus h. And there's one with a plus h.
Okay.
But any of those are the definition of the derivative. So if he asks for the definition, then you have to use the definition. This is not the definition. This is the quotient rule. But
Right.
if I had this problem, like if I had to do this by the definition, and then I had to do all of the other stuff that I have to do for this problem, because we haven't found the line yet.
Right.
We just found the slope.
The slope.
But now
You
now
can
we have
basically plug this into that equation, the line.
Well, no, because we need to know what the slope of the line is. And I don't have, hold on. I need to put the problem in front of me because I don't have it. Where did there it is. There it is. Oh, but I think that I closed that. Hold on. I'm sharing that. I thought I had it in. Oh, I never. Okay. So it says find the equations that are parallel to. So we want to be parallel now. Parallel to the line x plus 2y equals 2. So we need to know. So this is the expression for the slope. Now I need to be parallel to this line. Well, if I know that it's parallel to it, I need to know the slope of this line. So we need to find
y.
We need to find the slope of the line they give me, all right? So that's going to mean we have x plus 2y is equal to 2, right? And then there's a couple of ways to find the slope. Probably the easiest is to rearrange this. So you're going to subtract x from both sides, right? You get 2y is equal to negative x plus 2. Divide by 2. Each term, divide by 2. Okay? You get y equals negative 1/2 x plus 1.
Yeah.
So the slope of the line
1/2
is a negative 1/2. Now, what we have to do is we know that the lines are parallel. Now, since parallel lines have the same slope,
you set them equal to each other.
Slope. Parallel lines have equal slope, so we're going to say the slope is equal to negative 2 over x minus 1 squared, and that's equal to a negative 1/2. And we're going to solve for our x, and then we're going to find the lines after that. So that's why I said I wouldn't want to have to use the definition of the derivative to find the derivative, because then this problem would be even longer than it is. All right, so now I'm going to cross multiply. So I get negative 4 is equal to negative 1 times x minus 1 squared. And because I don't like those negatives, I'm going to just write it by multiplying a negative through. So I get 4 equals x minus 1 squared. And then I'm going to take the square root on both sides, keeping in mind that I have two solutions. So I have 2 is equal to the absolute value of x minus 1, or x minus 1 is equal to plus or minus 2. So x minus 1 is equal to 2, which means x would equal 3, or x minus 1 would equal negative 2, and x would equal negative 1. Now, that's not an equation of a line. That's the x-coordinate of a point. Okay? So now what I have to do is keep in mind that it's tangent to the graph. We have the slope. We know what the x-coordinates of the points are. So now we have to go back to the graph itself. Go back to the original y. Okay? Go back to your original function, y equals x plus 1 over x minus 1. And you have to find those points. So y equals x plus 1 over x minus 1. So for the value when x is 3, we get 3 plus 1, which is 4. So we get 3 plus 1 over 3 minus 1. So we get 4 over 2, which is 2. So one of my points is going to be 3, 2. Are you with me?
Wait, isn't it 4 over 2?
Right, but 4 over 2 is 2, isn't it?
2. Yeah, sorry, I thought you said 3 over 2.
No, I said the point is 3, 2.
Oh, 3, 2. Oh, okay, I see.
Because the point is 3, 2.
Point is 3, 2. Got it.
Right?
Yeah.
And so for the other one, where y equals negative 1, we get
It's 0.
Yes, 0 over negative 2, which is 0. So my other point is negative 1 and 0. Now, those are the points for which my tangent line is parallel to the line x plus 2y equals 2. So now I need to figure out what the equations of those lines are. So now I have the next part of this. So I know that I want to actually find the equations of my tangent line, okay? So I'm going to have two equations.
Okay.
And so I'm going to say that I know that m, because remember we said the slope was the same slope as the line. So the slope of the tangent is a negative half, right?
Yeah.
And for the first equation, it goes through the point 3, 2, right?
Yeah.
Because of the math that we did. So now this is where your point slope or your other version comes in handy. Y minus y1 equals m times x minus x1. So y minus 2 equals a negative half times x minus 3, right? And so I don't know what form he wants it in. He didn't say.
Yeah, he usually leaves it in this form, but he said, yeah, he says that if you're one of those people where your teachers like grained it into you to make it into the y equals mx plus b, then that's fine. He'll take that too.
Yeah, that's pretty much what every teacher and every class I've ever been in does.
Yeah.
They ingrain us to use this, but they want us to manipulate it. So, but I've noticed that he does that. So the second equation is m is equal to negative half because it's still parallel, right? But this one goes through the point 0 and...
Oh, it's negative 1, 0.
Negative 1? Yeah, I'm sorry, negative 1, 0. Yeah, I have to flip my page. You're paying attention. That's good. Y minus...
I told you mornings I'm like on it.
Y minus 0.
Okay.
equals a negative 1/2 x minus a negative 1, right?
Mm-hmm.
So we get, I'm just going to drop the 0. Y equals negative 1/2 x plus 1.
Yeah. So those are both parallel lines.
Well, they're not, yeah, they're parallel to each other, and they're also parallel to the line he gave you. So
Okay.
if I go in, let me see if I can do this.
That makes sense because they have the same slope.
Well, they should, because remember we solved for the variable, right? Remember?
Yeah.
So let me
So
see if I
sometimes he
can.
asks the it's perpendicular and you make it, he said, negative
It's
slope.
opposite sign and reciprocal. So what I tell my students is change the sign, flip it on its head. So if you get like negative 1/2, okay,
Mm-hmm.
change the sign, which would be positive, right, and flip it on its head. If you flip 1/2 on its head, you get 2. So it's positive 2 if it was the perpendicular line. So I threw the decimal calculator on the screen. Let me graph x plus 1 over x minus 1. So we have y equals x plus 1 over x minus 1. There's the graph of what he gave you. Okay, that's the original graph.
Okay.
Now, the line that he gave you was negative 1/2 x plus 1. So that's this. Y equals negative 1/2 x plus 1. Okay, that's this line. Okay, now what we want to do is find two tangent lines, okay, that are on this red curve, tangent to this curve, that are parallel to this blue line.
I see.
Okay, so of course, they're going to have the same slope as this does.
Right.
That's not the problem. We just don't know what x coordinates they'll be in. Does that make sense?
Yeah.
So they turn out to be, because we did the math already, they turn out to be at negative 1, 0 and at 3, 2. So if I plot those points, you have a tangent line at this green dot, which I'm going to draw right now, but that's one of them. And then the other one is at negative 1 and 0, which is, whoops, did it not? Oh, because it.
Comma?
Yeah, I put a decimal, so it was like waiting for the.
Oh, the point.
The other point. There it is. Okay. Now, so those are the places where the tangent line, I haven't drawn the tangent lines yet, but those are the places where the tangent line to the curve is going to be parallel to this blue line here.
Okay.
Does that make sense?
Yeah.
And that's what we just did with this. That's what we just did with our y equals mx plus b idea, or our, so we have y equals, let me do this one first, negative 1/2 times, oops, times No, that's not what I wanted to do. Okay, let me do it like this. I can do it the other way, but I don't quite know how to enter it all. So I'm gonna x plus 1. Still learning about this, but it makes it really nice. Now notice this. See this point right here? This -1, 0. See that? It goes through this point. This black line goes through this point. You see?
Yeah.
And it should. That was the point that we said. And notice this black line is parallel to this blue line, isn't it? You see it?
Yeah.
So one of the equations that we found was the equation for this black line. Now the other line is going to be y minus, okay, so y equals negative 0.5 times, I'm going to move the 2 over after
Okay.
x minus 3 plus 2. Plus 2, yeah.
Plus 2.
So there's my other line, and that's this dark red line right here. And so notice that the black line and this darker red line here are parallel to this blue one, right?
Mm-hmm.
And the black one and the red one up here are tangent to the curve that we had. And that's what we wanted.
That makes sense.
Okay? Does that help a little bit to see that?
Uh-huh. Yeah, it's just, sorry, I'm yawning.
No, that's fine.
So rude.
I totally, it makes total sense. Like, I totally understand you. Okay?
Yeah.
But I'll send you a picture of this too, but I'll send you a pic, let me scan it. But that's, if he had asked for perpendicular, then they would be coming this way through those points. But I don't know exactly if they'd be in the same places. They wouldn't be, they'd be different.
Right.
But that's a picture of what you're looking at. Okay?
So basically we found the quotient rule, we found the expression first for the slope.
For the slope of the tangent, right.
And we had said to find the slope from that equation.
Right, we need to know what the slope of the line is that they gave you, because
And
how are we going to make it parallel otherwise?
To that. Okay, that makes sense then.
I mean, how can we say, because there's an infinite number of tangent lines to that graph, right? And so we need to know where
that slope.
Exactly, which
Yeah.
line are we looking for?
Okay.
And there happen to be 2 lines because of the way this graph is. There happen to be 2 tangent lines that fit that.
Okay.
That fit that.
Yeah, it's just a lot of steps to remember, but I think I get it.
If you kind of remember the logic,
Yeah.
I wanted to do this on camera. I wanted to do it on Cam Scanner so I can send it to your email. There it is. Yeah, some of these problems take a minute to do. Some of them do take a minute. I grant you that. But it's not hard. It's just a lot of.
Yeah, it's just, I think, like you said, it's just like a lot of new information. So it's a lot to
And it's
learn.
all to process in.
Yeah, just knowing how to do. I mean, it's a good thing it's open notes and open book and all
Oh,
that.
really? That's all that's good for you guys.
Yeah, and he gave us a couple extra hours too, so we have 4 hours.
Oh, wow.
So I'm like,
I don't
well,
know if that's, I don't know if that's good or bad.
yeah, I know. I was like, okay, well, hope. I mean, some of these problems will take me an hour, so we'll see.
I don't think it'll take you an hour.
Yeah.
I mean, this problem, maybe 10 minutes, maybe 15,
Yeah.
but not an hour.
Yeah. I think just because of
This is
his
one of the
quiz.
this is one of the longer ones. You know what I mean? I mean,
Yeah.
some of them are not that bad. Um,
Yeah. He kind of reminds me of my chemistry teacher where he'll just pull out like this super hard problem to test your math skills, like, you know, see if you're.
Mr. Hugen asks some that are tricky sometimes, but I wouldn't say he picks the hardest, most impossible problem there is.
Yeah.
You know, like I really wouldn't. I would say that um, I would say that he picks the ones that are gonna help you like learn something, you know, to see if you learned it. But I don't. I think he's pretty good at like mixing the complexity too, because like some of those, like the first problem yesterday on the quiz was kind of long, but then after that they were a little bit shorter. Like number 2 looked
Yeah.
like it was going to be long, but it wasn't.
Yeah.
And then I think number 5 was a little bit long, but the rest of it, and number 7, but the rest of them, you know, he mixes it up so you're not like, oh my
Stuck.
God, I'm out of gas. Like, but I've run into a couple of Hugen problems once in a while that I really have to uh,
That's
just,
what I'm scared of.
you have to just crank through it. You know what I mean?
Yeah. Yeah, I asked him if he's going to be available for um, questions, like in case we have questions while we're taking the test.
Uh-huh.
And he's like, yeah, I can open my office hours just in case, like, it, for
In case
example, it's
there's like an error
impossible.
or something
Yeah, if
on
he
the
has like
off chance that there might be an error or
an
whatever.
error, right? Yeah, because that
It
was
can
my,
happen. It happens sometimes.
I know.
I remember, I think I told you about my statistics student that when he was taking this one quiz, that he's like, but I didn't study for that section because she didn't say we were going to have it on. I'm like, okay, let me look at it. Sure enough, it was there. I'm like, okay, I'll email her right now. And she did. She threw out the problem and adjusted the score.
Oh, okay.
And because she's like, I honestly, like, I forgot to remove it. Like, because normally she would test them on that, but we hadn't gotten there. So,
Yeah.
but she's like, everybody calm down. Just, you don't need to send me 15 emails. I'll fix it, you know, just relax. But, so she readjusted the points. But I mean, sometimes students get a little bit anxious. I couldn't blame them though, but I was like, yeah, I helped them with that once I realized that there was no way that he was going to be able to do it. And it wasn't his fault. He just hadn't studied it because he didn't know he was supposed to. But, you know, it happens sometimes. So it happens. But try not to make a huge up because it's not problematic. It's just there, you know.
Yeah.
What else do you want to work on? I'm
I've
emailing you.
made that mistake before, actually.
Oh, really?
Well, yeah, I got really stuck on this problem and then, like I just didn't move on. And then it took up like the whole test period just working on that one problem. And I learned from that. I was like, oh my gosh, I could have like um, failed this test because of that one problem. And then he ended up saying there was an error on it and he was gonna just give us full credit. So I was like, okay, if I get stuck, I'm just gonna circle it and move on because I don't want to
Yeah.
get stuck on them.
Well, especially if you think um, that it might be something um, that isn't related. You know what I mean?
Mhm.
I'm gonna send you. I think I.
So I think um, maybe we could do one of the limit ones, number 5,
Okay. Let
uh,
me
and then like you said, number 13 looked like
13. Sure. Let me save this and I emailed you the actual work. I'll email you the graph later.
okay.
I'm I'm going to have the graph also in case you go back and look at it, and then it's easier to remember kind of what we did. Let me stop sharing that. And I want to go, where do I want to go? I want to go back to file. 5, you said?
Hmm?
5?
5? Oh, the
Number
number.
5?
Yeah,
The
sorry.
limit?
Yes, number 5.
Oh, our
That's it.
friend the cubes. That's
Yeah,
why.
I think you would make that 8 into 2 cubed, right?
Mm, actually, here, since you're taking the limit, you're not going to be able to factor it out because of the h. Okay? So here, because of the limit, you want to expand it.
Okay.
You want to expand it and then try to crunch everything together and get rid of the h.
Okay.
So the limit, this is number 5. It says the limit as h goes to 0 of 2 plus h cubed
Minus 8
minus 8. Um,
over h.
uh-huh. Because otherwise, if you wrote it as the difference of cubes, you'd have 2 plus h minus 2, and then you'd still have an h left. You know what I mean? So it's better to actually expand this. So
Okay.
this is the other question that you asked me about memorizing the expansion for the cubes.
Yes.
It helps if you know it, but it's not totally necessary. But
Okay.
if you don't know it, then you're going to have to
Look it up and
expand it manually.
oh yeah.
So do 2 of them and then do the third one. So 2 plus h times 2 plus h is going to be 4 plus, be careful here, you have 2h and 2h, so that's 4h, right?
Mhm.
Plus h squared.
Yeah.
Then you're going to take that trinomial, put it in parentheses, and multiply by 2 plus h.
Okay.
So here you're going to get 4 times 2 is 8. 4 times h is 4h. 4h times 2 is 8h. 4h times h is 4h squared. H squared times 2 is 2h squared. And h squared times h is h cubed. So you get 8. Now, let's see. 4 plus 8 is 12. So you get 8 plus 12h. Plus 6h squared. Plus h cubed. Okay?
Yeah.
So then
U minus 8.
You get minus 8 over h. Now, the 8 on top, 8 minus 8 is 0, so they go away. Okay? And what I want to do is I want to factor out an h from the top. Factor out an h. So you're going to get on the top, if I'm going to write it in descending order first. I have h cubed plus 6h squared plus 12h over h. Then it's just easier to see it. The limit as h goes to 0. This is h. Factor it out, you get h squared plus 6h plus 12. You see?
So it basically is 12.
The limit is going to be 12, yes. Because at that point you have the limit as h goes to 0 of h squared plus 6h plus 12. And if you plug in 0, you get 12.
Okay.
Okay? That was number 5.
The way you would write that answer, would I write limit h goes to 0 and then I write equals 12? Is that like how I would write it?
I wrote the limit of h goes to 0 of h squared plus 6h plus 12
Equals.
is equal to 12.
Okay.
Once you plug in the value, you don't have the limit anymore.
Right.
So if you wrote, I'm going to write that down below here and send you a picture of it. Limit as h goes to 0 of h squared plus 6h plus 12. And if I plug it in, then I drop the limit. So I get 0 squared plus 6 times 0 plus 12 equals 12. So let me just shoot a quick picture of the bottom part.
Oh, can we also do number 7 and number
7? Sure.
Yeah.
Yeah. Let me just make sure that it's.
Sorry, I just want to do a few of these just to get them.
No, you don't have to apologize. It's fine.
Okay.
It's what you hired me for, Sam. So, let's see. No, that's not what's here. There it is. Picture too large for crossing. Okay. Oops. Trying to send it to somebody else. How dare you? Don't be afraid of that calculus. All right, number 7, is it?
Yes.
Okay, let's see if I have room. I have room on this piece of paper. Let's see if I have room on the back. Maybe. What is the number? Oh, that's gonna be interesting.
Only because I was thinking with that absolute value on the bottom too.
Right. And notice that you have the limit as x goes to 3/2. Right?
Yeah.
So what does that mean? You have to make sure that the limits on both sides are the same, right? So we're going to have to do 2 problems here. Because the that absolute value is going to be different, right?
I see.
So that one is a little bit, there's an extra piece to that limit. So I'm just getting more paper. You're right to be suspicious of it a little bit. So, did you get I sent that picture to your phone since we had already done the problem? The one that we just did, number 5. Can you see what I wrote?
Yeah.
So number 7 says the limit as x approaches 3/2 of
2x squared.
2x squared minus 3x over the absolute value of 2x minus 3. Now, we have to note that in order for the limit as x approaches 3/2 to exist, the one-sided limits should be equal, right? So we also need to note that the absolute value of 2x minus 3 is a piecewise function, right? So it has a dual definition. It's 2x minus 3 as long as x is greater than or equal to 3/2, and it's 3 minus 2x if x is less than 3/2. Are you okay with that?
Yeah.
You're okay
Wait,
with
as long as x is less than, you said?
So it's equal to itself without the absolute value bars.
Uh-huh.
X is greater than or equal to 3/2.
Okay.
And it's equal to 3 minus 2x if x is less than 3/2.
Okay.
Right?
Yeah.
So now, if I'm approaching, so let me find the limit as x approaches 3/2, but from the right through values that are larger. So that's the top one, right?
Okay.
So the limit as x approaches 3/2 from the right of 2x squared minus 3x over the absolute value of 2x minus 3 is going to equal the limit as x approaches 3/2 from the right of 2x squared minus 3x over 2x minus 3, which is the limit as x approaches 3/2 from the right of, I'm going to pull out an x on the top. So I get x times the quantity of 2x minus 3 over 2x minus 3. My 2x minus 3 is canceled, so I get the limit as x approaches 3/2 from the right of x, which is 3/2. Okay? So the right-sided limit is 3/2.
Okay.
Was that too fast for you, or did you?
No, that's good.
Okay, so the right-sided limit is 3/2. Now let's do the left-sided limit. So the limit as x approaches 3/2 from the left of 2x squared minus 3x over the absolute value of 2x minus 3 is equal to the limit as x approaches 3/2 from the left of, I'm going to factor out an x again. Well, before I do that, let me write this as 2x squared minus 3x. And the bottom of this now is going to be the opposite, so it's going to be 3 minus 2x, yes?
Yes.
So then I'm going to say the limit as x approaches 3/2 from the left. And this time I'm going to factor out an x from the top. And I have 2x minus 3. The bottom is 3 minus 2x. So then I get that's equal to the limit as x approaches 3/2 from the left. Now you have to be a little bit careful here. Remember, when you have 2x minus 3 and you have 3 minus 2x, they cancel but with a -1. Remember that?
Yeah.
So if you want to show the step, you can write x times 2x minus 3. And on the bottom, write it in descending order. So write -2x plus 3. Then write your limit. Limit as x approaches 3/2 from the left. And you do x, 2x minus 3. Factor out a -1 from the bottom. You get 2x minus 3. Then they cancel, and you get the limit as x approaches 3/2 from the left. And that would be -x, right? So the limit as x approaches 3/2 from the left of -x would be -3/2, right?
Yeah.
Now, since the limit on the left and the right are not the same,
Does not exist.
the limit does not exist. The limit as x approaches 3/2 of 2x squared minus 3x over the absolute value of 2x minus 3 does not exist. So that's your final answer. But you have to show the limits. Anytime you have a piecewise function where the limits could be different, you're going to have that. You're going to have to check to see any time that there's more than one way for the function to be defined, you're going to have to check that. And I think that's the case in one of the other problems later where you're asked about continuity, if I remember correctly. I think there's like a C and you have to find the value of C that makes it continuous or something like that.
Yes. That's
I think that's like 18 or something like that.
Number 13 or
13. I'm going to send a picture of what we just did to your phone. Because you did it with me, so
okay.
I think you should be able to follow. But the other one, the tangent line one, is in your email. So which one would you like to do now? We did number 5. We did number 7. Which other one would you like to do?
Maybe the one below number 9.
9? Okay. Let's see what number 9 looks like. So number 9 is, okay, this is the squeeze theorem. Prove that the limit as x goes to 0 of x squared sine 1 over x is equal to 0. So the limit, so we're proving that the limit as x goes to 0 of x squared sine 1 over x is equal to 0, right? So, okay. I don't know how much you know or remember about the squeeze theorem lecture.
Yeah, not so much. I know he talked about it the last class, but I don't really remember.
Okay. So what you have to do, and this is where Desmos is going to help us. So let me bring up Desmos again here and share the screen. Let me get rid of add item. No, it's not what I want to do. Hide expression list. No, I want a new graph. How do I get? Do I have to close it? Maybe. I'm not sure, but I'm gonna close it and see what happens. I have to learn more about how to use that, so I know what.
Are you talking about the Desmos?
About the Desmos on the desktop.
Oh.
I don't know much about the program, but I discovered that it's really handy if I need to make graphs and explain stuff, you know what I mean?
Yeah.
It's fine if I'm pushing calculator buttons and whatever, but if I need to actually explain the graph, this online Desmos is a lot nicer because I can make it do stuff. I just don't know much about what it can do, you know?
Yeah.
I've never used it before, but I kind of like it, but I'm still learning to use it. So, all right. So when you're trying to prove the squeeze theorem, okay, basically what you're trying to do is squeeze the function that you're looking at between two functions that you know the limit of. Okay, so you start by looking at the graph of whatever the trig function is, y equals, and this isn't part of the proof, this is part of helping you understand what you're looking at, okay? So the sine of, because it has to be, you have to know what, okay, so what happens here is that this curve oscillates like crazy in the middle, right? So it goes to here, it starts here, and then it oscillates like crazy, and then it goes like this, right?
Mm-hmm.
Well, now he might do it a little differently, so I'll have to go and look at the lecture to make sure. But basically, we start with the fact that we know that the sine of x, not the sine of 1 over x, but the sine of x is between -1 and 1, right?
Yeah.
Well, then it makes sense that the sine of 1 over x, because my x is now 1 over x, right?
Mm-hmm.
The sine of 1 over x would have to be between -1 and 1 also, right?
Right.
So what we try to do is we're looking at the sine of x. Now we have the sine of 1 over x. So we know that the sine.
And you don't include the x squared in that?
Not yet.
Okay.
I start with the fact that I know that -1 is less than or equal to the sine of 1 over x, which is less than or equal, because it is. If you look at the graph, let me put in the line so you can see it, okay? If I put in a line y equals 1,
yeah,
right here, that's y equals 1, right? And then I put in the line y equals -1 right here. See the green one?
mm-hmm.
And we know that because the argument of the sign, what comes out, the argument of the sign can be any real number normally. Now here it's going to be restricted. It's not going to be x can't be 0 because it'll be undefined. There's that little red asymptote. I don't know if you can see it, but it's asymptotic at that point. But the sign itself has to be between -1 and 1, right?
Yeah.
So now what you do is you say, we know that the sign of x can be between, a sine of 1 over x can be between -1 and 1. Now, we know that since x squared is always greater than 0, right?
Yeah.
It's always positive. We can multiply the entire inequality by x squared. Yes?
Mm-hmm.
So, since x squared is always greater than 0, we can multiply the entire inequality by x squared without changing the direction, right? And this is going to become important in a second. This is where you asked me about the x squared, and we're getting to that, okay? So now if I multiply the whole inequality by x squared, I get -x squared is less than or equal to the sine of 1 over, is equal to, hold on, I wrote it wrong. -x squared is less than or equal to x squared times the sine of 1 over x is less than or equal to x squared.
Okay, that makes sense.
So now we've got this inequality. And so now remember, the squeeze theorem says that if I have y equals x squared, let me put x squared in here. There's x squared, the blue line, right? Mm-hmm. And if I have y equals -x squared, okay, then
it's going to be flipped upside down.
-x squared. Yeah, but I want to show you the, right here. You'll see what's happening. See right here? We're looking for it around 0, right? And so what's happening is this limit is going to 0, obviously, right? Mm-hmm. This black curve. This limit is going to 0 here. And the curve is squeezed between them at that point. At 0, the curve is between it, right?
Yeah.
So what's happening here is that then I can say that the limit as x goes to 0 of -x squared is 0, and the limit as x goes to 0 of x squared is equal to 0. And since
it's between, it has to be 0.
X squared times because actually we're doing, now we're looking at this. We're looking at x squared sine x, right? So now we're looking at that curve, right? Because we multiplied by x squared, yes?
Yes.
Let me hide these. We don't need these lines anymore. But now, this blue curve and this, see how the red curve is squashed between it?
Yeah.
So now, and since x squared times the sine of 1 over x is between the two, functions, right?
Mm-hmm.
The limit as x goes to 0. Now, he might write this a little differently, but this is pretty much the way I was taught to write it, so you'll kind of have to go back and see. And I'll look on the lecture today after we leave to see what it says. The limit of goes to 0 of x squared sine 1 over x must be 0. Does that make sense?
Yes.
So let me take a picture of that. And not a picture, but a screenshot. And then I'll send this to you with my other
Thank you.
with my other curves. But I know the squeeze theorem was tricky for me. I had to spend a lot of time in Professor McDowell's office going over that.
I know, that's one that I'm going to have
But
to.
she had a really good way of doing it, though. So it would actually, and she didn't give us the hardest problems. She just wanted to make sure we knew
Like, understood
what the theorem was about. And I'm like,
right.
that was so much easier than when I tried to do it the first time. Sometimes it's amazing what like one person's explanation will do for you. Like, oh, I never realized that was problematic until but it's like what time is your appointment? I don't want to keep you. It's 9:48. I can go for a while longer.
Yeah, I think I'll call it quits right now, and then when I come back, I'll just see what you're doing.
Let me just send you before you, and then I'll send you the other part too. But I'll send the others to your email. But I just want to make sure you get the picture of what I just.
Bless you.
Not necessarily the picture of the Desmos. I'm gonna attach that all with your video when I upload it. So I'll attach the screenshot.
Okay.
And then the other. But the pictures, I want to make sure it went to your phone. If we did it together, then I just sent it to your phone. You know?
Okay.
But if you had trouble doing it, like the first one, I cam scanned that and sent that to your email.
Yeah, I think because I wrote it as well, I should be able to pick up where.
But if not, then like I said, it's there.
Okay.
But I think that this one helps, right? So you understand what we did in terms of the difference between, because you have to make sure you know what the domain is. Mm-hmm. And then once you establish that it's always positive, you're looking for the limit.
Yeah. Yeah, that's where I'm going to have to maybe
Well, you can always replay the video. I'm recording it, so.
Oh, okay. Okay, good. Yeah,
it might come in 2 parts, though, like the other one, because we got disconnected. Mm-hmm. So I'll upload it in 2 parts, and then you can watch it if you need to rewatch.
Okay.
That part. Okay?
Thank you. I appreciate it.
Of course. You're welcome. Thank you for letting me practice my calculus today.
Of course.
No, because it's going to help me, like.
Yeah, that's good. I know. When we come back, if we can also maybe take a look at number 13.
Is that the one with the, hold on, let me see.
That's with that.
That is.
Piecewise.
Where it's continuous?
Mm-hmm.
Where it's continuous? I think Professor Nadell gave us this, but I think our X was different.
Yeah, because I've never seen it where it's like CX plus 1.
Well, okay, so basically what you need to do is find the C so that the function is continuous, right? So it has to be defined at C, right?
Mm-hmm.
And where is the problem? Where's the point where you're going to have a problem? If you have a problem at all, where is it going to be? At what X?
CX squared minus 1 is greater than 1, so at 1?
No, 13 is 3. So if you're going to have a problem with the continuity, you're going to have a problem where the X changes.
Oh, 3. Right.
Because the definition is different, right?
Okay, right.
So it's defined at 3 already, right? Mm-hmm. So that's not an issue. But you have to basically take the limits on both sides, and then you have to solve for the C that makes the limits equal to each other.
Okay, we might have to do that one together.
But the one thing that I want you to know is that when it's piecewise, like this, the places where it's broken or where it's piecewise, and you could have more than one, you know what I mean? Because it could be like from -1 to 2, it's this. From 2 to 3, it's, you know what I mean? Sometimes there's more than one place where it changes. But if it changes definitions, those are the places where if you have problems with continuity, you might not, but if you do, they're going to occur there.
Okay.
Because they're going to be potentially places where the function has a different definition than it should. Now look at 12. If you didn't have this part, if it said, where might the function be discontinuous, where would I automatically be suspicious?
At 4.
At 4, because the definition changes.
Right.
At 4, right? And here it's obvious to see that this function has a discontinuity there because this is not defined at 4, right? And even though they define it, they fill in the hole, right? In other words, it may be continuous, but we have to check the limit for that.
Okay.
Okay, so that's what I wanted you to see. So the point to be suspicious of on 13 is at 3.
Okay.
You have to check what happens on both sides of 3 to see what the value should be. But that's another story for another.
Yeah. Okay.
All right, then.
All right. Thank you. I'll talk to you soon.
All right, Sam. Take care. Hope good luck with the plumber today.
Oh, thank you.
Hope it doesn't cost too much money.
I know.